All right, so welcome to our video on geometric sequence. So earlier we had talked about arithmetic sequences, and geometric sequences are similar, except for where an arithmetic is related by addition, a geometric is related by multiplication. Now, a geometric sequence is a numbered list of terms with a defined starting point. So that's again our first term, which we'll call U1, where the terms are related by a common ratio. And so that common ratio is the number you would need to multiply by to get from here to here. And that should be the same as the number you need to multiply to get from here to here, and the same as the number you need to multiply to get from here to here and from here to here. Well, let's just check. To multiply something by 18 to get to 6, it's going to be 1/3, and we give that the number r. So we say that r is 1/3. And let's just do a check. 54 times a third is 18. 13,122 times a third is 4,374. I know that because I checked it on my calculator, or I did long division because I'm a champ like that. So these are our values. Now, just like in our other look at sequences, it is interesting to be able to describe the general term. So like if we just continued this on, what would the nth term look like? Well, un is going to be given by your starting term, and then because we, at each point here, we multiply by r, and we multiply by r again, and we multiply by r a whole bunch of times. I think that you can see that this is going to be a repeated multiplication or a power. So un will be u1 times r, and if I have n terms all the way up to here, then I'll have multiplied by r n minus 1 times, because I didn't multiply by r here. I multiplied by r the first time to get to u2. So for example, u2 is equal to u1 times r, so it has a power of 1. U3 is equal to U1 times R again, or just U2 times R. And so what I end up seeing is the exponent is 1 less than the term number. So that's where my exponent of n minus 1 comes in my general formula. So I now know my general formula, and that's a geometric sequence. So suppose this sequence ended right here. That was the last term. So it went from here to here, and that was the last term. And I wanted to figure out how many terms. So how many terms are in the sequence to 6? I'm just going to assume that we're talking about this top sequence. This isn't a very well phrased question, but it'll get across the point. Basically, I want to figure out, okay, if I know U1 and I know R, and I know that this is the last term, how many terms were there? Now, I suppose you could just go ahead and start dividing with your calculator, but suppose you didn't have a calculator, or suppose you just didn't want to do that, and you wanted to do it a more efficient algebraic way. Well, we start off with the general term. Un is equal to u1 r to the n minus 1. And we know that 6 is the nth term, so 6 is equal to, now u1 is 39,366, r is 1/3, and this becomes n minus 1. And now our goal is to solve for n. Now, by golly, doesn't that look like a exponential equation? Good thing we've just solved those. So the first thing we'll do is we'll isolate the exponential term. So we'll have 6 divided by 39,366, and that'll be equal to 1/3 to the power n minus 1. Now 6 goes into 39,366. I'm going to guess 6,000... 6,511 times, but I'm not sure. So I'm going to take out my calculator. 6,561 times. Darn it. So this is 1 over 6,561 is equal to 1/3 to the power n minus 1. Now, if you know your powers of 3 really well, then you know that 3 to the power 8 is 6,561. So this is 1 over 3 to the power 8 is equal to 1 over 3 to the n minus 1. And now we can drop the base. So 8 is equal to n minus 1, and n is equal to 9. So there would be 9 terms the whole way along. And of course, at this point, you're saying, hey, Gregorius, I could have just divided my calculator a bunch of times and got there faster. You're right. But what if it was 93 terms long? Well, then, Gregorius, I wouldn't know that this is to a power 93. I say, of course, you're right. But what if we, instead of solving this by finding this with a common base from here to here, we instead use logarithms? So the base is 1/3. The value we want to get to is 1 over 6,561, and we set that equal to the exponent, n minus 1. Now, a quick trick on your calculators, and we'll press Math, and we'll scroll up 1, and we'll see that log base is A. So we'll choose log base, and we'll type 1 divided by 3 as our base, and 1 divided by 6,561 as our value, and that is going to be equal to 8. I don't know if you can see it. So we would have 8 is equal to n minus 1, and once again, n is equal to 9. And even if we didn't know our powers, to get from here to here, if we didn't know our powers, we could just use logarithms to get there. So that's a geometric sequence. Darn it, I almost got it through this video without making that mistake.